In the last class, we have discussed about the mean and the variance of a random variable. So mean of random variable x, represented as x bar or denoted as e of x, is integral of x into px dx, and of course the variance sigma x square was defined as e of x minus x bar square. Okay, and we have seen that how we can compute the mean and the variance if the probability density function of the random variable is given to you. Okay, today we will discuss a random variable that is ultimately important in the theory of communication, which is a Gaussian random variable, and later on they will extend it to the Gaussian random process, or maybe white Gaussian noise, what we call it. Okay. So Gaussian random variable is defined using a PDF, which is px of x as 1 by under root 2 pi e raised to power minus x squared by 2. So this is a Gaussian random variable with a zero mean value, mu x is 0 and sigma x square is 1. Okay, with a zero mean and a constant variance. And in general, you can define the Gaussian random variable as 1 by sigma under root 2 pi e raised to power minus x minus m square by 2 sigma square, where the mean is m and the variance is sigma square. Okay, and if you see, the entire Gaussian PDF is basically dictated by just two quantities. One is sigma and one is m. Okay, the mean and the variance, they completely define a Gaussian random variable. Of course, it is a special case with a zero mean and a variance that is unity. And in general, if you plot the Gaussian PDF, suppose you have px of x and x. If it is zero mean and unity variance Gaussian random variable like this, then it is a bell curve like this, okay, which has a mean of mu and which has a variance that is sigma square, which is 1. Okay, this is also called as normal distribution. And if you plot this Gaussian random variable, a general Gaussian random variable, which has a mean value of m and a variance of sigma squared, so it can be something like this, depending upon the value of mu and sigma. So this is mu of x, which is equal to m, and this will have a variance which is sigma. Okay, so this bell curve is a very important random variable. Okay, the Gaussian, which we call as a Gaussian random variable. Now we will certain things. First, we will see that whether it satisfies the property of being a random variable or not. Okay, so for that we have to simply see that the area under this should be unity. That is the first condition. The area under the probability density function is unity, that already we have discussed. So if I define p of x, if I define px of x as 1 over root 2 pi e to the power minus x square by 2, and to check whether this is basically a PDF or not, we have to just integrate it minus infinity to infinity px of x dx, and that should result into unity. The area under this curve is unity. It can be taken as a probability density function. Okay. So if I integrate this function minus 2 plus infinity 1 by square root of 2, which is constant, I can take it outside the integration, e raised to power minus x square by 2 into dx. Okay. So what I need to find is the integration, this integral e to the power minus x square by 2, or in general I can find the integral of e raised to power minus x square dx, and based on this integral you can compute e raised to power minus x square by 2 dx. What will be the integral of this? Okay, and this integral is equal to under root of pi. Okay, so you can prove it. Suppose I take this integral as I, then I can take I square as integral of minus infinity to plus infinity e raised to power minus x square dx into integral of minus 2 plus infinity e raised to power minus y square dy. Okay, so it should be also here e to the power minus x square dx, because it is a product. I square is I into I, and I is this integral. But since x and y, they both are dummy variable, you can change the variable from x to y. Okay, and then it becomes a double integral e to the power minus x square plus y square into dx into dy. Now at this point, we change the coordinates from rectangular coordinates to the polar coordinates. So I can represent x square plus y square as r square. Okay, so if this is x coordinate and this is y coordinate, so this is r, this is theta, so x is r cos theta and the y component is your r sin theta. Definitely your r square will be equal to x square plus y square, or you can say r is the square root of x square plus y square, and similarly we can find theta in terms of x and y, that is tan inverse of y over x. So if I use the polar coordinates, then this double integral will become e to the power minus r square, because x square plus y square is r square, and this dx dy will be converted to r dr d theta, and the limits for theta will be from 0 to 2 pi, and r will go from 0 to infinity. Okay, because if x goes from minus infinity to plus infinity, and y goes from minus infinity to plus infinity, your r will go from 0 to infinity, definitely. Okay, but theta, which is this angle, it can only go from 0 to 2 pi. So that is why the limit for theta will be from 0 to 2 pi, and the limits for r is from 0 to infinity. And this dx dy will be replaced with r d theta dr, because if you see dr d theta, maybe I suppose say this is dr is the incremental change in the radius. I say this is a very small value, that is dr, and similarly d theta, this is d theta, which is the differential change in the angle. Okay, and likewise in the rectangular coordinate system x and y, you have dx dy. So this is your dx and this is your dy. Okay, so dx dy basically defines the area of a small rectangle in the xy plane, where dx and dy, they are typically very small. Okay, likewise, so we basically, when you replace the coordinates of the system from xy to r theta, so this area which is represented by dx and dy here, this will represent it here with this part, approximate it. So you have to multiply this dr with the length of this arc, and the length of this arc will be basically r d theta. Okay, because length of the arc divided by the radius of circle gives you the angle theta. So this I can say dl, which will be r d theta. So this angle is basically length of the arc divided by the radius. Okay, and this length will be equal to r d theta. That is why you are getting here r dr d theta. Now you can integrate it, and if I integrate this function, I can put this r square as maybe x, or suppose variable u, then definitely your 2r into dr will be equal to du by taking the derivative on both sides, or you can say that r dr will become du by 2, and this integral will converge to 0 to 2 pi. You can have d theta 0 to r, so 0 to infinity. You can have e raised to power minus r square, which is now u, and r d dr, that becomes du over 2. Okay, so if you evaluate the outer integral, it is integration of d theta is theta, limits from 0 to 2 pi, you will get 2 pi minus 0 multiplied with 1 by 2 into integration of e to the power minus x is e to the power minus u with limits from 0 to infinity, of course minus 1. Okay, so e raised to the power minus u du, if you integrate it, the integral of e raised to the power minus u is e raised to the power minus u, but when you take the derivative of minus u, it becomes minus 1. That is why you have multiplied it with minus 1 here, and then it becomes 2 pi into 1 by 2 e to the power minus infinity, which is 0 minus 1, so you get as pi. Okay, so this we have taken I square, so I square is pi, definitely I, which is this integral, it will become under root of pi. Okay, so if it is under root of pi, so now you have integral of minus 2 plus infinity e raised to power minus x square dx as square root of pi. But in the Gaussian random variable that we have defined, with 0 mean and constant variance I am taking. It is 1 by root 2 pi e raised to power minus x square by 2. And then you have to take the integral of this function. If you take the integral of this function from plus to minus infinity, you get e raised to power minus x square by 2 dx. And you already know what is the integral of minus 2 plus infinity raised to power minus x square dx. It is now under root of pi. So in this, if I replace x square by 2 with variable y, then definitely not with y, I need here x square. So I can write it as 1 by root 2 pi integral of e raised to power minus x by root 2 square into dx. Okay, and then I replace this minus is outside, sorry, and then I replace x by root 2 as y, then your dx will be under root 2 dy, and this integration will become 1 by root 2 pi minus 2 plus infinity e raised to power minus y square into root 2 dy. So root 2, it will become 1 by under root 2 pi into root 2, and e raised to power minus y square dy, this will become under root of pi. Okay, so ultimately it gets cancelled and you get 1. So integration of the PDF that we have defined as a Gaussian random variable with a 0 mean and a unit variance is 1. Okay, so that is one thing that we have just defined. The second thing that you can do is that you can find the mean and the variance of the random variable, which is more generalized. That means mean is m and the variance is sigma square. So you have p of x, which is 1 by sigma under root 2 pi and e raised to power minus x minus m square divided by 2 sigma square. So this I am saying that it is a random variable which has a mean value of m, and the variance of this random variable is sigma square. Okay, so if you find the mean of this random variable x or x bar or mu of x, whatever you write, it is integral of x into px of x dx. Okay, so that I can write as integral of x into px of x as this function. So 1 by sigma under root 2 pi you can take outside the integration, it is a constant. Okay, m and sigma both are constants, into e raised to power minus x minus m square divided by 2 sigma square into d of x. Okay, so by making some change in the variables, if I suppose write x minus sigma by, if I write this, if I replace x minus m with a variable, suppose y, then definitely your x becomes m plus y, and this integral which is E of x, will become 1 by sigma under root 2 pi integral of minus 2 plus infinity. X will be replaced as m plus y or y plus m, whatever you write. Y plus m into e raised to power minus should become y square by 2 sigma square into dy. Where m is constant, so dx is equal to dy. So if you further expand this, you will have two terms. One is 1 by sigma under root 2 pi, that is of course constant. You will have one integral minus infinity to infinity y e raised to power minus y square by 2 sigma square into dy plus m integral of e raised to power minus y square by 2 sigma square into dy. If you look to this integral is basically 0 because this is the odd function. Okay, if I say this is a function of y, as y e raised to power minus y square by 2 sigma square, then f of minus y will become minus y into e raised to power minus y square by 2 sigma square, and that I can write as minus of f of y. Then f of minus y is minus times f of y. We have an odd function, and the integration of odd function is 0. So this term, the first term, this multiplied by this, it becomes 0. Okay, plus m, and then you have this integral. This is again in the same form, e raised to power minus x square dx, but we have to get here x square. So for that, I can replace this y by maybe under root 2 sigma as suppose x, then this becomes e power minus x square. Okay, and dy will of course become root 2 sigma into dx. This will become 1 by sigma under root 2 pi multiplied with m, because this term is now 0, integral of minus 2 plus infinity e raised to power minus x square, and dx is under root 2 sigma into dx. dy is this. Okay, and if you take under root 2 sigma outside this, then e raised to power minus x square dx integral is under root of pi. Okay, so ultimately you get sigma under root 2 pi divided by sigma under root 2 pi multiplied with m. So this gets cancelled. You'll see that the mean value of this random variable is m. Okay, so the Gaussian random variable that we have defined like this, it basically has a mean value that is equal to m, and likewise you can find the variance. Okay, to find the variance of this random variable, it will become sigma square. So that we will discuss in the next class.